We should be familiar with Coulombs' law from last year. Coulombs' law deals with forces due to electric fields. And just like all forces, there has to be two objects interacting, or two fields interacting. And this is just like the universal law of gravitation, where the force is due to gravitational fields of the two different masses that are interacting with each other. And the equation for Coulomb's law is very similar to that of the universal law of gravitation. And r is the center-to-center distance. And the force of two electric fields interacting is another constant K times the two charges divided by that center-to-center separation squared again. You can see the similarities. K is equal to a constant 1 over 4 pi epsilon naught, which we'll start to see that in the later chapters. But the value of K is approximately 9 times 10 to the 9th. We looked at situations like I have here to the left in gravitation. So we have three charges interacting with each other. The difference between electric forces and gravitational forces is the type of charge determines the direction. Whereas all masses attract, some charges repel. So if Q1 is negative, Q2 is positive, and Q3 is positive, we have to determine the vector direction of the force in whatever particle we're looking at. So let's look for the force on charge 2. We know that like charges repel and opposites attract. So Q1 is going to attract Q2, and Q3 is going to repel Q2. We also have to know the distance between these charges. We'll make them both the same value as some R value. Now with multiple forces, we just have to sum them up vectorially. So we have the force of charge 1 on 2 and the force of charge 3 on 2. And we substitute in our values into the Coulomb's law equation. Now, since the force on 2 from 1 is to the left and the force of 3 on 2 is to the left, those are both negative forces. And you can see a lot of common factors that you can take out to help simplify the problem. And if we had the values, I'm sure you can handle it from there. And you can get the net force on charge 2. So let's look at a situation where we have a charge distribution in two directions. All right, so we have 4 charges. It's a square where the sides have length of r. That'll be charge 1, 2, 3, and 4. And we want to figure out the force on Q1 due to the other 3 charges. We have to know the charge value of each of these. Now we examine how the forces are going to act on Q1. So Q2 is going to attract Q1. Q4 is going to repel Q1. And if we say that all of the charges are the same, then the force from 2 on 1 is going to be the same magnitude as the force from 4 on 1. Now Q3 is going to attract Q1, and that is going to be less force than the other two because it's at a farther distance away. We set up the equation with the sum of all the forces, and we can see that if we just look at the x direction, we only have two forces that have components in the x direction. So we have to the left the force of 4 on 1, and then we have the component of 3 on 1, and the distance diagonally is going to be the square root of 2 times that distance. But we also have to figure out the component. Since this is a square, we know the angle is 45, and it's the x component, so we're going to use the cosine. We also have to sum up all the forces in the y, and here Q4 exerts no force up and down. So we just have Q2 on 1, and that is downward, so that one's going to be negative. And we have Q3 on 1 as well, and that's also down, which is going to be negative. And if you look at this, you can pull out a few common factors. To make your math a little easier so you don't have to multiply the same numbers over and over and over again. But that's, I think, as difficult as it's going to get, besides solving for the angle that the net force is pointing. And again, we always use the inverse tangent of the y values over the x values in order to get the angle with respect to the x-axis.